Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So how does optimized environmental sensing help address the challenges of information overload? The challenges of the next decade, I think, are huge with respect to the environment, partly because of our reliance on non-renewable sources of energy, which causes severe pollution problems leading to global effects like global warming. And I think a question that we should ask ourselves as computer scientists is, what can we do to help with these challenges? What small steps can we take to help in this direction? And since this was part of a talk that I gave at ICHCAR, which is the largest AI conference, the way that I posed it there was, can we build some AI heroes that can help us address the challenges of the coming century? So here's a small step in this direction. Monitoring algal blooms. So when pollution levels and other kinds of, mainly nitrates in water, increase a lot, algae can grow out of control and have devastating effects. And this is a severe problem that's happening all over the world. So this example in China, about 4 million people were affected, 1,300 factories closed, and $14 billion of cleanup cost was involved. And this is happening everywhere, and we really don't understand why. Why is this phenomenon happening? And I think that AI methods and computer science methods can help us model, understand, and prevent things like this, large-scale algal blooms. And again, small step in this direction is a collaboration that we've been doing with a group at UCLA and USC who have really cool robots. This is basically a sensor on a boat that moves around the lake and makes measurements in order to try to make predictions about why these contaminations are happening and how they spread. And again, a small step in this part of the problem is the question that we can only make a few observations in this lake because of limited resources on the boat. And we want to do this as well as possible. So we want to be able to optimize those in order to make predictions about the pollution all over the lake. So where should we sense in order to make the most accurate predictions? So what we're going to talk today about is this kind of optimization problem. How can we optimize what data we gather, what experiments we do, and many other kind of applications of this form. And I'll talk a little bit more about that. So let's talk about another example, the pipes that bring water to our taps. This is called water distribution systems. And if you have a contamination in the system, it can spread and affect thousands or millions of people. And we actually do something to try to prevent this right now. Do we know what we do? Yes? No? Thoughts? We actually put some chlorine at the source of the water, and we sit at home and hope for the best. This is our strategy. And because this strategy might not be the optimal one, a group of civil engineers all over the world is trying to address this problem. So in a collaboration with a group here at Carnegie Mellon between computer science and civil engineering, we've been thinking about how to instrument the systems with sensors in order to detect contaminations, which is pretty exciting, I think. The problem is that the sensors are expensive. They cost about $14,000. And we can't imagine a local government spending money on this. And it's such a big issue that there was this competition where we got a model of a city and a simulator from the EPA, the Environmental Protection Agency in the US, and we had to go back and tell them where to place the sensors in order to most quickly detect contaminations. So these are two examples of sensing the environment to understand things better or to prevent problems in the environment. We can also ask ourselves, how can we help address environmental challenges? In other words, how can we make better personal choices, more informed personal choices that allow us to have a better impact personally on the environment? And if we want to do that, our first step in this process might be, for example, going to Google. Sorry, I should have said going to Bing. And
what's your favorite search engine? Whatever it is.
Yes, going to Bingo and typing in a query like carbon footprint. And you get about 4 million answers back, and maybe you don't know even where to start. And for every kind of challenge you might want to address, like renewable energy or recycling and reusing and so on, there's millions and millions of bits of information out there I don't know where to start. I don't know what I trust. I don't know what I should read. I'm overloaded with information. So here, I think we can also help by understanding the structure in this information, picking out the most important sources, and being able to make better decisions in this case. So we can imagine that the problems we're trying to address can fall into this kind of category. I want to learn something about the world, how to decrease my carbon footprint, or how to predict algal blooms, from a limited set of observations, which are expensive, so I want to do this as cost-effectively as possible. And this is a fundamental problem, which is, what information should I use to learn about the world? Fundamental problem that we face every day. And so, in this fundamental problem, we can imagine trying to build solutions for it. So for monitoring algal blooms and optimizing that information, we can build, again, since it was an AI conference, I said an AI hero for that. And on the other hand, for collecting information from the web, we can also build another hero for that. And for every type of similar problem, we can build a different hero for that, I guess, and try to solve that problem, a different solution for each one of these. And the issue here, and maybe the computational thinking issue, is that each one of these, building each one of these solutions takes us a lot of time and a lot of effort, and it doesn't scale to try to build one solution for each of these problems. So a question we might ask is there a narrow waist? Is there a common framework that allows us to solve many of these problems under the same umbrella, and thus have an impact not just in one area, but in many areas of science and beyond? And I think to do this, we might discover and exploit key structure in the problems that allow us to scale up to these really large, challenging tasks. And since these tasks are both challenging and important, they've been around for quite a long time from different fields with different names. And I would say that in a very broad stroke, the solutions fall into one of two categories. Either heuristics, where you can't prove anything about the solution, and they might do arbitrarily bad in practice, or methods that try to find the optimal solution, but don't scale to large problems. And because of that, we usually had point solutions rather than this global narrow waist that lets address many problems at once. And what we've been working on, and this is mainly work of my student Andreas Krause, who is now a Caltech prof, and a number of other students, is on designing approximation algorithms with theoretical guarantees so you can prove something about them, and they scale to a number of real application domains. And so what I'll talk about today, since this is a short version of the talk, I'm going to give you an idea of what kind of structure we discovered in these problems, and then I'm going to focus on the implications to a number of different application domains. So to do that, I'm going to use a running example. My running example is going to be water distribution systems, the pipes that bring water to our taps. If you have a contamination at a particular location and it's a bad location, it might spread and affect a lot of people here. I'm going to label that node as red. One that affects fewer people, I label it as yellow, and one that affects almost nobody, I'm going to label as green. And so you can imagine coloring the map this way, depending on where the contamination would enter the system. And so if I put a sensor somewhere, I'm going to detect some of these contaminations earlier. And something that would affect a lot of people, a red node, might become yellow or green. And the optimization problem here is to select a set of locations A such that most of the map gets green or something intuitively. Or in other words, there's some function f of quality, and for this set A, I might get 0.9 points, while for some other set that is not as good, I might only get 0.01 points, and my goal is to pick an A that gives me as many points as possible. So this is the optimization problem I'd like to solve. By the way, if I wanted to maximize F, what is the obvious thing to do?
More sensors.
Just put sensors everywhere, right? And since we might not have money for that, we want to solve what's called a constraint optimization problem. So we're going to say, I'm going to select a set of locations A, that maximize my sensing quality F, subject to a constraint that my cost has to be within my budget. This is called constraint optimization. And I can ask myself, is constraint optimization the kind of narrow waist that we're trying to find to solve many of these practical problems? And to understand whether that's a narrow waist, whether that's the solution we're looking for, then let's look at the simplest version of this problem. We'll consider one of the simplest ones, where I'm just putting case sensors into the environment. So I want to maximize F, and I'm putting case sensors. So the way I always think about this is I buy case sensors, and I want to go and put them out in the environment. So I guess I buy it at Kmart, because that's where they sell K things. So even the simplest version of the problem is already NP hard. So thinking about just general constraint optimization is not a narrow waist at all. It's an intractable kind of narrow waist. And what we have to do is discover more structure that would allow us to solve these problems better, more effectively. There must be more structure there that can be exploited. And to understand this extra structure, let's look at the simplest possible algorithm I can take for this problem. And here's this famous greedy algorithm. I put a sensor where it gives me most information. Then I put a sensor that gives me most additional information, and I keep iterating until I run out of sensors. This is a simple heuristic. It runs in polynomial time, so it maybe not solves an NP-hard problem. And the question is, how well does this simple solution do? And here's some truth in advertisement, right? If you're a researcher, you might say, I'm going to try the simplest possible thing, because then I'm going to come up with this fancy algorithm that's going to make me famous among my colleagues or something. And it's going to do much better. And if you take small problems that can be solved optimally by exhaustive search, and you compare the answer from the greedy solution to the optimal solution, you see that the answer is very close. Right? There's not much gap. So when the gap is so small, you're not going to get that famous. So if you can't improve it, maybe you can understand it. And by understanding it, maybe you can learn something about the world that's kind of interesting. And as we try to understand why this simple solution performs so well, we looked and discovered that it had a particular property, a particular diminishing returns property that's present in many practical applications. So this is one slide that captures the type of structure that we're going to be exploiting in many of these real applications. It's called submodularity. Intuitively, if I have 2 sensors in a deployment versus a larger one of 4 sensors, intuitively, adding an extra one helps me more on the small problem than it does on the larger problem. In other words, if I have 2 sets A and B, adding an extra element S prime to the smaller set helps me more than to the larger set. When this holds, we call it a submodular function. And it turns out that water distribution systems and many other real applications satisfy this property, this diminishing returns property. And if your problem satisfies this diminishing returns property, beautiful things happen, I must say. So here's the simplest thing that we learn from an old result by Nemhaus et al. It says that the solution obtained by the optimal intractable algorithm, the NP-hard solution, versus the greedy algorithm that we couldn't beat, is guaranteed to be at least 63% away. Usually much better than 63%, in practice much better. But what it says is, even before you run it, you know the greedy is going to perform pretty well. And in fact, this is going to be the best possible solution you can have in general, unless P equals NP. So what we've understood is that by detecting that these problems have this particular property, we could explain for simple ones why they perform so well. And that's why submodularity was important. And it's important for many other reasons. And to explain one, let me go back to the water distribution systems competition that we participated in a couple of years ago. So we got a model of a city with about 12,000 nodes. It's a real city from the US. And a simulator from the Environmental Protection Agency. There's about 3.6 million possible contamination events that they cared about, and they wanted to do well on average, for an average contamination in the city. A number of groups from all over the world participated. Some used genetic algorithms. This is how well they did. Some used other heuristics. Some said, forget algorithms. I've been working on this problem for 20 years, and I know exactly where to place sensors. I call that domain knowledge. That's how well they did. Some try to solve it exactly or approximately exactly using mixed integer programming. This is how well they did. There's a curve missing, and this is us. And it's about 24% better than best runner-up. So how did that happen? Was it just because we proved the theorem? And in fact, that's not it. So there was about 3.6 million possible contamination events, and computing F was extremely slow. Exhaustive search was totally infeasible. Even the greedy algorithm was slow. It took about 30 hours for one of the settings in the competition, and there was 30 different settings, which required about 6 weeks of computation that we didn't have. But submodularity is not just about proving theorems. It's also about designing algorithms. So one of the things that we did was to design an algorithm we called SELF that has the same theoretical guarantees as the best possible algorithm, but it's much faster. It uses lazy evaluations that makes it much faster, and it runs instead of in 6 weeks, in about 2 days worth of computation. And that's what allowed us to scale to large problems, and that's what allowed us to solve the problems that were setting in the competition. So if we step back, we talked about this narrow waist in the beginning, and I think that what was the spinach in some sense for me, or the structure that allowed us to solve it, was this notion of submodularity. So the narrow waist that I'm thinking about is constraint optimization of submodular functions. So if we think about water distribution systems, we can think about what we've done so far is come up with a solution which is good for an average possible contamination in this system. So if we take an expected value over possible contaminations, we can do pretty well, which leaves us with an obvious open problem, which is if I put my sensors out and an adversary can see where they are, they're going to say, oh, here's your weak spot. I'm going to contaminate right here. And maybe you'll suffer a lot. So you want to be robust against such an adversary. Or in other settings, for example, when you're optimizing the path of a robot in a lake, we might optimize with respect to what we know about this lake right now. But something might change. There might be some dynamics or a wind of change might change the conditions a little bit. And our model might be incorrect, but we still want to be good with respect to such perturbations. So these are two settings where you want to do robust optimization, not just the regular optimization that I talked about so far. And so I'm going to very briefly mention this problem and then go back and talk about information overload and how these all fit together. So in this problem, you can imagine if I have a set of sensors A over here, an adversary might come and contaminate me at location 1. But because it's nearby, I can detect it pretty well. So F1 of A is high. On the other hand, if an adversary were smart, he wouldn't contaminate me at 1, he would contaminate me at 2, because F2 of A is low. And since we are optimizing for the worst case, the minimum of high and low is also known as low, I guess. Well, if I had a good set of sensors B, we get that both F1 and F2 are high. And so the minimum high and high turns out to be high. And what we really want to do is have a set of submodular functions Fi, one for each possible contamination locations, and optimize for the worst case the adversary might pick, the minimum. And even though each one of these is submodular, we can think about using our spinach here, the minimum of submodular functions is not submodular. So the question is, what do we do about this? And one thing we can think about is the greedy algorithms have served us well in the past. What happens if we try it here? And here's an example of what happens if you try it. I might have 3 objects in the world, the racket, the guitar, and the apple. And this, it's an example inspired by my student Andreas, who is a good racquetball player, but an amazing guitar player. So you can imagine you have 2 kids, F1 and F2. One likes the racket. F1 likes the racket, doesn't care for the guitar, likes the apple a little bit. The second doesn't care for the racket, likes the guitar a lot, and likes the apple a little bit. And if you're being greedy, the first object that you buy to make both kids happy, at least a little bit, is the apple in this case, because somebody's going to be unhappy if you don't buy the apple. And if you're greedy, you pick that first, and then in the next step, you're only able to pick the racket and the guitar, the racket and the apple, and somebody's going to be unhappy, and your total score is epsilon. While if you're optimal, you pick two objects, racket and guitar, you get an optimal score of 1, and you have a gap between epsilon and 1, which turns out to be very large, arbitrarily large, the gap between epsilon and 1. And so maybe the greedy algorithm is bad. And maybe you say, you only know the greedy algorithm, which may be true, I only know that algorithm. And you think you can come up with something better. And I would really encourage you to do that. Because if you could come up with something better, that is, if you could come up with an algorithm that gives you any approximation guarantee whatsoever, even exponentially small approximation guarantee to this problem, of placing case sensors to optimize this robust objective, then P equals NP. So we cannot find a solution to the problem that I posed a few slides ago. Or maybe we can. And I'm not going to tell you what a solution looks like because of the short period of time, but I'm going to tell you what the difference was, what the insight was. And our insight was the following. This problem of placing case sensors was hard. But if we relax the problem a little bit, we design an algorithm we call saturate that achieves the same optimal solution as placing case sensors, but uses a little bit more than k, uses alpha case sensors, where alpha is some logarithmic factor. So it's kind of like, I bought a house recently, a contractor comes to your house, you tell them, go put me 10 sensors. They say, no problem. 2 months later, they said, I got it, I did it for you, but I used 12 sensors. It happened with my flooring in my house. They used 20% more or something. And basically, this is what's going to happen here. And if you could come up with a factor that's better than ours, if you can find out that beta that's better than my alpha, then NP-hard problems can be solved in n to the log n time. So it's unlikely that you'll be able to improve this algorithm. So let me show you one practical application of this, and then we'll close off with information overload questions. So when I go to a lake with this robot in order to detect algal blooms, we can imagine going around and making some measurements. But if we optimize for the average possible error in this lake, there might be some location in the lake that has large error. And that location might be the key location to understand why algal blooms happened. And so instead for optimizing for the average case, we might want to optimize for the worst case prediction throughout the lake, which is this robust submodular sensing problem that we just described. And in spatial statistics, this is called the minimax Kriging problem. It's a problem that's been around for a long time, and the state-of-the-art solution was a simulated annealing approach with 7 free parameters that somehow somebody tuned by hand. And our algorithm has no parameters to tune. And here's a picture of Andreas at a lake collecting data and doing experiments. If you try the greedy algorithm on this problem, it doesn't do too badly. If you try the simulated annealing state-of-the-art, it does better. And ours does about the same. On another data set, again, greedy doesn't do too bad. Simulated annealing does better. We do about the same as state-of-the-art. And we were 10 times faster with no parameters to tune. But I claim that these problems, these 2 instances, were easy because greedy didn't do so badly. And I told you that greedy could do arbitrarily badly. If you look at water distribution systems, here greedy does terribly. It gets nowhere, as the theory predicted. Simulated annealing does better, but gets stuck no matter what you try. While saturate does better and keeps on getting better, getting about 60% better solutions. So, stepping back a little bit, we talked about constraint maximization of submodular functions being a narrow waist that exploits this common structure. When we're placing case sensors, the greedy algorithm was near optimal, even though this is an NP-hard problem. While in robust settings, the greedy algorithm was terrible, but something like saturate provides a near optimal solution. And in other related settings, again, by exploiting the fact that you have this structure, submodularity, you're able to scale up to large problems and prove things about your solutions. And at submodularity.org, we have a tutorial and papers and a MATLAB toolbox that you can use if somebody is interested. So these are all applications that I've described that involve physical sensing, where I'm trying to learn something about the physical world. Now let's jump to something totally different. So let's go from water to the web. In 2008, it was measured there were about 184 million blogs out there. And about 77% of the people who use the web read blogs. How many people read blogs here? It's about 77% of the people. I'm that smart. It's computational thinking right there. And this is such a huge amount of information that even Time magazine had an article around the same time that asked how many blogs does the world really need? Which is a pretty good question. And so you can ask yourself, if I have 10 minutes a day to spend on the blogosphere, which one of the billions of blogs should you read in order to stay on top of big stories? Now, let's try to formalize this problem a little bit. So if you have an important story, very important story in the blogosphere, then it's first posted, for example, in the machine learning theory blog, of course. Then it gets picked up by Slashdot, Boing Boing, and so on, and spreads through the blogosphere in what we call an information cascade. And if you are unlucky enough to read Boing Boing instead of the machine learning theory blog, you might capture the story over here, and these people here learn the story after you. And so you can think about a big blog is one that learns about these big stories as early as possible. Seems like a totally different problem than what we've been talking about so far. But in fact, it's not. Stories spreading through the blogosphere is very similar to contamination spreading through water distribution systems. They're both about these cascades, and fundamentally, they're both about the optimization of some modular functions. So the same kind of ideas, the same kind of algorithms work in both places, which shows this idea of narrow waist. So just quantitatively for a second, if you read random blogs, you do really badly. So don't read random blogs. I don't recommend it. If you use the kind of heuristic that people use out there, like the number of inlinks to a blog, you do better. But if you use this kind of formation we have, you do quite a lot better. And these problems are huge. We're dealing with a huge amount of data. The greedy algorithm is infeasible, but this lazy evaluation self that I didn't describe but mentioned is about 700 times faster, and is able to scale up the dimensions of data that we have to deal with here. And so it's actually, I think, a pretty exciting thing to see all of these algorithms being used in another domain. And what it allowed us to do is go from 184 million blogs to K important blogs in the blogosphere. But the fact is, there's a lot being talked about in the blogosphere, and there might not be a set of blogs that capture your particular interests. So you could turn the story around and say, out of the million postings that I'm getting a day from an agreement with a startup, right now I'm getting about 1 million postings a day, which one should I show you? And if I show you what's being most discussed, you might get postings like this around 2008 this time, lipstick on a pig. I imagine some of you remember this. And while you might think this is important, think about what was being talked about, but not as prevalently at the same time. And if you think for a second, you realize that the other topics in the blogosphere that were being ignored, there's something like the start of our economic crisis. And so just talking about what's being discussed right now, it's interesting, but you might want to think about what stories should you read based on your personal interests. What's good for you? And so let's give an example of that. So this is a system we call turn down the noise in the blogosphere to try to find important stories for you. So if we pick a particular day on January 17th, 2009, what this word cloud is showing is the bigger the word, the more prevalent this topic was discussed in the blogosphere. Do you remember what's happening in January 17th, 2009? Obama inauguration. Yeah. What else? The Israeli-Gaza conflict was starting out, and something happened in New York. A plane landing in the Hudson River, right? So one thing that we do is if you just get onto the system right away, what you get is a set of stories that just pick up what's being most commonly discussed and just covers that. And these were the stories of that day. But what's important to you might not be what's important in general. So, for example, this is what's being discussed that day. But if you were Zidane, everybody know who Zidane is? You might care about the fact that Barcelona creamed Man United. Yes, anybody know what that's about? Or some other sports-like stories. And from this feedback, you might get stories that personalize to Zidane, like something about Manchester City Football Club, the Steelers, or the sports-related stories. And so the idea here is we start from the blogosphere, we get a notion of coverage, which gets optimized to show postings what's out there, and you can sit back and enjoy because that's submodular function optimization. But from your feedback, I can personalize. I can learn a notion of coverage that changes your coverage to personalized coverage and gives you personalized postings that cover your particular interests. And we can do that. And we actually, if you go to turn down the noise, you can see a demo of our system. It's online right now, turndownthenoise.com. And so just to close, we started with this idea of constraint maximization of some modular functions as being narrow ways. And I showed you for some environmental sensing applications that it was useful in several ways. Now, when we looked at the blogosphere, we were able to use the same algorithms but get new insights. So, for example, placing case sensors was like finding a needle in a haystack, finding good postings for you. While the notion of sequential sensing, which I didn't discuss too much today, is the notion of personalization that we discussed in terms of the blogosphere. And so I'll just close off with a quick anecdote. We were working on this problem of optimization, and we were working on monitoring pollution in lakes and rivers, which I thought was pretty important, but never got any press or anything. We built a smart chair that could be used by the elderly to help them with their posture. Again, that got nothing. We won this competition about the water distribution systems, and that got nothing. Then we said, what else can we do? And just to close off, I'll tell you what happened. We did this thing with the blogosphere, and we put a list on the web of 100 blogs you might want to read. And that took off the blogosphere. Lots of people were saying, this is so cool, I'm on the list. Then other people were like, this is meaningless. I'm not on the list. And other people writing analysis of what they should do to get on the list next year. And there was some news and so on. Pretty interesting. So let me close off by saying, exciting stuff happens when you think about these narrow ways and these kinds of algorithms. Thank you.